Yay, okay, we're getting started. Continuing on, but first, circling back, I kind of flubbed this whole thing about current, which is like one of the most basic things. And my decision is forget physics. Physics just confuses everything. But I actually, what this is actually trying to say for those is I'm pretty interested in this. So I have, in the new version, I'm just taking out all these physics equations and just keeping the math equation. That's all we really need is I equals dq dt. And you just count the number of charges that go by a wire over a certain amount of time. And the charges divided by the time is the current. Now, I can explain sort of the physics, or I can show you enough that you don't care anymore. Question? Yeah, beats the hell out of me. But let me show you, I did look up, this is my textbook. My textbook that I bought, and I was so annoyed how expensive all these textbooks were, and I just bought it anyway. And I still have it 31 years, actually 34 years after I took the class. And you should have your books 34 years from now as well. Yeah, this is my physics book from physics. No, it's from MIT. Yeah, and it was actually a very slim book. Here's the picture. It's actually falling apart. It was probably like $30 back in 1983 or something, you know. Yeah, Berkeley Physics course, volume 2, and confused the hell out of me. Physics, you know, it's just so annoying. And you know, this is why it's annoying, because look what they do. They don't talk about current through a wire. They talk about just a bunch of charges floating through space, you know. And they can't like have rectangles. They have to have these rhomboid things. Because for some reason, you know, the U doesn't have to be in the same direction as the plane of the A, but you know, you do have charges, you know, flying through these hoops and everything. And here's the formula. I still don't know what NE is, you know, the formula on those slides, which is crazy. But this is basically the formula here, and it basically just says, and you know, what's kind of funny is because this may seem like we're making a big fuss out of nothing, which is like basically what all of physics is. Because really, the ideas are quite simple. So, yeah, basically it's talking about a volume of charges and, oops, that's my Hawaii picture. That's a, that's a nose job I got while I was in Hawaii. I knew that would come in handy somewhere. Anyway, so that's charge, and thank God we're not doing physics. You can't do anything with physics; it just confuses you. But you know, we are going to bring in some physics every now and then. It's not terrible. It is actually pretty cool if you take it in small quantities. So we talked about charge. We did a couple problems, and now we're going to look at voltage, another really fundamental aspect of electricity, of circuits, voltage. And this actually involves the kind of physics that's actually kind of makes sense. The idea of work, you know, you got all this in physics 3A. The voltage between points A and B is the work done or change in energy by the electrical system in moving a unit charge from A to B. So that would be considered VAB. And so that's the change in work divided by the number of charges, right? How many charges you're elevating with a certain amount of energy. And that's essentially what a battery is doing or a voltage source is doing. It's providing energy to charges. So the definition of a volt is 1 joule, which is where the energy comes in. applied to a coulomb of charge. That's the charge. That's the dq. So if you take a coulomb, take 6 times 10 to the 18 electrons, and inject them, somehow give them altogether a joule of energy, that requires a volt to do. So yeah, so that's the definition of voltage, and we'll be seeing that all over the place. It's a very, it still seems kind of abstract, but it's very similar to potential energy, which we're going to look at in a second. A really good analogy of voltage is just regular gravitational potential energy, and we'll explain why that's so. The plus and minus signs are important and another source of confusion, but they're used to define the reference direction of the voltage polarity that you're doing it. And what I think about that is, again, they're just pluses and minuses. What does that actually mean? Well, this is why the lab is really important, because when you hook up a voltmeter to a circuit, which you'll be doing over and over again in the lab, you've all played with voltmeters in physics 3B, right? And there's 2 ports, right? There's a V port, and there's one, what's the other one called that you hook up the wire to? Yeah, but they call it something else. Common, right? So it's called common, okay? And that's like the reference polarity of the voltmeter. And if this is like a 9-volt battery, right? And you hook up the plus wire to the plus wire of the plus terminal of the battery, and you hook up the common to the minus terminal of the battery, what voltage do you think you're going to read on your voltmeter? And you've got the power turned on. Turned on. Yeah. Anyone have another number besides 0? You're going to see 9 volts. Okay? Now watch very carefully. This is how complicated it is. It's like a magic trick. What happens if I hook the wires up the other way? I hook the minus sign, the common of the voltmeter, to the plus side, and the plus of the voltmeter to the minus side. You're going to get negative 9 volts. What does that mean? Yeah, well, when it says 9 volts, that means the plus side of the voltmeter has 9 volts more energy than the minus sign of the voltmeter, right? And when it says minus 9 volts, what does that mean? It means the plus side of the voltmeter is sensing 9 volts less energy than the common point. Common point is at a higher potential than the plus side of the voltmeter, right? That's what that means. So that is sort of why we fixate on these things, right? If you hook up your voltmeter the wrong way, you're going to get a negative result than what you might be thinking, right? So you actually always have to pay attention to those signs. It's super important. 90% of the mistakes people make are because they frickin' screw up these signs. Yeah. What does the negative sign where mean? The negative sign of the voltmeter. That's just a common point. That's a. So the thing about potential is you always have to choose a reference node. You always have to choose a point in your circuit that you're going to say, well, we're going to call this 0 volts. It's not necessarily really at 0 volts relative to some absolute sense in the universe. Who knows what the voltage is relative to the center of the universe or the center of the Earth, right? It could be anything. But we're just going to say, we're going to call this our reference voltage. And then we're going to see what this other voltage at another point in the circuit is relative to that reference voltage. And the one we call the reference voltage is the common point. It's where we happen to stick the minus sign of the voltmeter, the common point of the voltmeter. And normally, just to kind of, because we don't like to confuse ourselves, normally we hook the minus sign of the voltmeter up to the minus side of whatever voltage quantity we're trying to look at, given the plus and minus labels. And we hook the plus sign up to the plus sign. So if you see 9 volts on the voltmeter, what does that mean again, Ollie? You have no idea, right? Yeah. So it means point A has more energy, has 9 volts more energy relative to the energy at point B. Can you say that for me? Yeah. 9 volts more energy than point B. Yeah. Yeah, that's what that means. Isaac? Uh-huh. Yeah, they're sensing that, right? So that potential energy difference is being communicated to the voltmeter, and the voltmeter is actually sensing it. That's why it says 9 volts here, because the plus side of my voltmeter is 9 volts higher than the common side of the voltmeter. There's higher energy there. And that has significance about which way current's going to flow, right? Because positive charges flow from the high potential side to the negative potential side, because of the difference in energy. But what that really means is the electrons are flowing the other way. You want to really confuse you? Think about which one has the higher energy from the point of view of electrons. On a 9-volt battery, which side has more energy from the point of view of the flow of electrons? The negative side. Yeah, that's where the electrons are coming out of. They have higher energy there. That's what's really happening. But we actually flip it, and we have the plus side. Sorry? Whose fault is it? I don't know. Yeah, Franklin or somebody. Yeah, we'll have a hate Franklin day, a day of rage. So point A is at a potential of VAB higher than B. Now VAB could be a negative number. This could be a negative 9-volt source, right? So then the plus side could have a negative, could be below the minus side anyway, right? So that's all. These are all possible. And the potential point A with respect to V is VAB. And if you flip it, that's what I was just saying here. If you flip the wires around, then you get an opposite side. So the analogy, and it is helpful to have these mechanical analogies because energy is something that we use a lot of in mechanical systems. So the change in energy due to gravity is very similar to the change in energy due to electric potential. So like if you have a mass here at point 1, and it's some height 1 off of the ground, it has a potential energy at point 1 of mg h1. And if you take that same mass and move it up a hill, so point 2 here, it now has a height of h2. And the potential energy at this point is mg h2, right? And we never really know what the absolute potential is in anywhere in a circuit. You never know what that is. You only know the difference. So we can only tell the difference in energy between these 2 points, right? So this would be, you know, the potential difference from 1 to 2 is the change in potential energy. And in this case, that would be m times g times h2 minus h1. And this would be the analogy of sort of like similar to like VAB, right? It's sort of like looking at the energy at 2 different points in your circuit or 2 different points on a hill, the energy changes, right? And it's the same idea. Okay, so that can help because masses, what do they want to do? They want to go downhill. And charges the same way. They want to go down to a lower energy level. So when you give them a high energy, what are they going to want to do when you let go of them? They're going to go down into a low energy. They want to go through wires and your circuit components to get to that lower energy state. And in the process, they're going to release energy. And that's really what's going on in these circuits, just the flow of energy from one point to another through these electrons. Okay. So speaking of energy, we spend a lot of time because a lot of circuits is about transmitting power from point A to point B. Why do we have lights, on? How do our computers getting power? That's really important. power is the time rate of expending or absorbing energy. And the definition of power is dW dt. And that's an interesting term. It's a change in W over change in energy over change in time. And you can take this and multiply it by dq over dq. And since V equals dW dq, you can sort of rearrange terms a little bit. And in this formula here, you can see how dW dt can be expressed as dW dq times dq dt. But dq dt is also familiar, right? This is our V. And what is this? That's current. That's I. So it just sort of falls out. It's pretty wild. But power is current times amps. I mean, volts times amps. Current times voltage. P equals V times I. This is where physics is actually pretty cool, right? It all sort of comes together. It just happens. It's pretty wild, but not confusing at all. It's just really simple. Okay, one thing that you're going to have to puzzle over, and this is going to be on quiz 1 next Sunday, not this Sunday, but next Sunday. You're going to have to master this by next Sunday, is passive sign convention. Passive sign convention is one of these things that it's really simple, but you got to like focus on it long enough so that it sinks in, because otherwise you're going to just keep making mistakes over and over again. Basically, you have a 50% chance. If you're asking the question whether power is being delivered to or absorbed by an element, you know, randomly, you have a 50% chance of getting the right or wrong answer if you don't understand what's going on here. But if you understand it, you'll get it right 100% of the time, whether something is absorbing or delivering power to a circuit. And that's the same thing like, you know, your car battery dies, you hook up a, you know, your friend's car battery to your car battery while you charge it. You got power flowing. Which way is power flowing? Well, it's presumably flowing from the car with a good battery to the car with a bad battery, right? There's a direction of flow there. That's why that's important, that we understand which way the direction of the power is actually going. And that's what this passive sign convention is going to help us nail. We're going to get it right every time if you absorb this. This simple lesson, passive sign convention. And there is a protocol here when you're dealing with a device. And what happens is you label the terminals plus and minus, and then you label the current. The direction of the current is indicated by an arrow. And again, we're talking about the flow of positive charges. And what passive sign convention says is when the current arrow enters through the positive terminal of the element, you have to use the formula P equals IV to determine the power associated with that element. And whether that answer is positive or negative indicates whether the device is absorbing or delivering power to the circuit. If it's positive, that means the device is absorbing power. If it's negative, it means the device is dissipating, is providing power. Yeah. Yes, an element is referring to a part of a circuit. In this case, it's this little box here. Yeah. That box is a circuit. It could be a battery. It could be the battery that you're trying to charge in your car, or it could be a resistor. Yeah, it's an unmarked box, an unknown element. And we don't care. All we need to know is what's the voltage at the terminals and what's the direction of the current. And from those two things, you can tell whether power is flowing into or out of this box. And that's really good to know, right? And this is use P equals IV. When current arrow enters through the negative terminal, use P equals minus IV, okay? And what this is, you know, when you think about passive sign convention, it's so easy. Just go back to this thing, right? Which direction is that box going to want to go? It wants to go downhill. Boxes want to go from high potential energy to low potential energy. And that's passive. You know, it doesn't take any energy to do that. It's going to release energy. It's just going to fall downhill. Anybody can fall downhill, right? That's just passive, right? But to actually go uphill, you got to push it up. That's sort of active. It takes energy to do that. Well, it's the same idea here. What this is saying that when you have the arrows and the polarity written this way, this is saying that charge is flowing quote downhill, right? What's downhill in the context of circuits? From the plus side, the high energy side, the high voltage side of the element, to the low energy side of the element, right? And it's just saying current is flowing from the high energy side to the low energy. Well, that's pretty easy. Anything can do that, right? That's what it wants to do. Current wants to do that. That's passive. So we call that passive sign convention. And what this is saying is current is flowing uphill, right? Charge is flowing. According to our conventions. And that's why we have to say P equals IV or P equals minus IV. This doesn't actually say here. So right here, under here, you're going to say P equals plus I times V, right? And when this, and so basically you have to really, you're looking at these things, right? This is the important thing, right? Current is flowing into the plus side of this element, right? That's the key. And if you see that pattern, you got to say P equals plus IV. When you see this pattern, current is flowing out of that element through the plus side, you got to use this formula, P equals minus IV. You're going to practice this with the quiz, so you're going to get this right. The practice quiz is going to help you nail this. It's really important. Okay. And then the last thing, though, is that, well, you know what? Both I and V, they're just variables. So, in fact, I could be negative 5 amps, and V could be negative 10 volts. So the underlying quantity really matters. If they're both positive, right? So suppose, and here's an example here. Let's make a little table here, right? So here's I, here's V, and let's put a box so that what we're talking about is the passive one. So in other words, we're going to use P equals IV. That makes sense? So we're not going to look at the right side now. We're just looking at the left side. And so suppose I is 5 and V is 10. What's the power? If you're looking at the left circuit, right, with those orientations, you got to say P equals I times V. So that's 50 watts. And what does that mean? Is it absorbing or releasing power? It's absorbing, because the P is greater than 0. That means the element is absorbing power from the circuit. Right? Means the battery's getting charged if that's the dead battery in a 2-battery circuit, right? But what if, when you hook up your voltmeter, you find, oh, the current is actually minus 5 amps, even though the voltage is 10 volts. What is the power? Minus 50. So what does that mean for that component? It means that's actually the good battery in the circuit. That's the battery that's providing the power. It's sending power into that circuit out of those terminals, right? So it's delivering power. It delivers power, right? What if both I and V are negative? It's minus 5 amps and minus 10 volts. What's the power? 50 watts. What does that mean? It's back to being absorbing, right? If they both flip, then you still have that same situation where the current is falling down from the positive, high energy side to the negative, low energy side, right? Okay? That's what you got to get clear on. Not that hard. You all can do it. It's basic algebra, whatever. You all can do it. Okay, I did, I used to have a ton of these things I stripped out because I wanted to kind of keep things short, but But these are actually good problems. When you look at these components, you can ask yourself, is this component, and forget about what these things actually are. They're all different things. This is a current source. That's an unknown box. This is a battery. That's a resistor, whatever. We're going to talk more about what these things are in a moment. But this is what you got to do. You got to look at A and you got to say, are those arrows indicating the situation for active sign or passive sign? The arrow relative to the plus sign. Is that active or passive? Sorry? Passive. No, it's not. What do we say about passive? Passive is, I'm going to erase all this stuff again. Look at this. Here's passive sign on the left. Did I even indicate that? Why don't we put this in? This is passive sign here on the left. Passive sign is when charge enters the plus side of the device, right? This here is active sign because the current is leaving through the plus side. Now look at this thing. Tell me what's happening. Is current entering or leaving that device through the plus side? It's exiting that component through the plus side. That's active sign. Right? Because it's active sign, so you're going to write active here. Do active sign, right? Then you got to use the formula. What's the formula you got to use? P equals what? Minus I times V. Because it's active sign. Does someone say positive? You look at the wrong one, right? It's easy to mess this up, but you got to hold these. You got to keep that in front of you when you do these things, right? P equals minus IV because of active sign, right? It's just simple pattern matching. It's all you got to do. So what's the answer? It's minus 25 watts, right? Is it absorbing or delivering power to the? It's delivering, right? It's delivering. Anyone want to argue about that? I'm ready for it. Yeah, question? Uh-huh. Well, we're talking about a battery, right? And it is the natural flow for a battery. But what is a battery doing? It's adding energy to those charges. So it's actually adding energy, and that energy leaves the battery and goes off into the circuit. It's delivering energy to the circuit. Okay, what I associate with the battery is somebody standing at the bottom of a hill, pushing a box up the hill. That's what a battery is doing. How does the box get up the hill? Somebody's got to push it. That's what the battery's doing through chemical reactions, and that's chemistry. I'm not going there, right? That battery is adding energy to those electrons. And over time, the battery dissipates itself. It runs out of energy. So you got to recharge it, right? Yeah. But while it's doing that, it's adding energy to those electrons. And they come out with a high energy. And they can then go do work somewhere else in your circuit. They can turn on light, they can illuminate light bulbs. They can heat up your room. They can drive your car if you have an electric car. Isaac. Will it always be absorbing and passive and supplying an effort? No, the sign is just, the active and passive sign is just to tell you which formula to use to figure out the power associated with that device. When you get the final number in watts, if that number is positive or negative, that determines whether it's absorbing or delivering power to the circuit. Negative watts means the element is providing energy to the circuit. Yeah. It's absorbing it. Yeah, yeah. Just arbitrary, right? Show positive current. Okay, well, this arrow is indicating the flow of positive current, so positive current is going that way. And which side has the higher voltage, higher potential? This side, right? This is the higher potential, right? That's the higher potential side. Okay, do the rest of these right now. Yes. You don't have this? Oh, really? Dang. Well, just write them out. Yeah. Shoot, I got to add these to the handouts. I probably added this last year because it was really helpful, and yeah, they didn't get it either. But it's really worthwhile. This is the really. This is what it comes all down to. You know, if you. Well, let's look at B while you're doing this, and we don't have to draw them all first. Let's just look at B now, because it's really not that hard, right? What's the sign convention for B? Is it passive or active sign? It's passive sign. Good. So you can write passive sign. And therefore, what formula do you use? P equals plus IV, right? And in this case, that equals, power is going to be, was that 1.8? Something like 1.8 watts, right? Okay. Is it absorbing or delivering power? Absorbing. So that is a symbol of a battery. When do batteries absorb power? When you're getting them charged. Yeah. When you hook up your phone to the charger at night, it's absorbing power. Current flowing into the high energy side, building up energy in there, right? So it is absorbing. The direction of positive current is down, and the higher energy side is excuse me. All right, well, just to kind of mess with you, right? Now you got one with a whole bunch of minus signs in it. Okay, but you still go to the basics. So C has minus signs everywhere, right? Look at the, you know, and you can even ignore this. You're looking at this guy relative to this guy, right? The quantity here is minus 16 volts, but our sign here is labeled on the bottom with a plus sign, right? But we're looking at the relationship between these two, and what does that indicate? Does that indicate passive sign or active sign? Passive. Current is flowing into the plus side. Well, no, what I said is you're looking at the arrow relative to the plus side of the device. Those are variables though. And this is what the third step means. Both I and V can be positive or negative values. But if you set up the formula right, the math will actually work out just fine. Yeah. Yeah, what I'm saying is think about it in small steps. Because if you try to do everything at once, you're gonna screw it up, right? The small step is look at how the arrow relates to the plus side of the labeling of that device. And that says passive sign convention, right? Cameron? Yes. Uh-huh. Again, when it's absorbing power, probably, yeah. Yeah. Mm-hmm. Yeah. Anything's possible. I'm not sure what your hang-up is. Oh. Mm-hmm. Well, I mean, well, why don't we just continue the problem? Because at the end, we're gonna talk about these showing the higher V and the positive current, and that will probably clarify things, right? Because that's showing you the underlying reality. But for now, passive sign convention means we got to use P equals IV, and I is -4 and V is -16. So it's -4 times -16, which is 64 watts, right? It's positive, therefore, this device is what? Absorbing power. Now, positive current is actually, in reality, going down, right? Because you have an arrow, and basically that's just showing the reference. Like when you measure current in the lab too, you've got a reference direction, and if the current's flowing opposite to your reference direction, it's going to show negative current. It just means it's flowing the other way. So you really have 4 amps flowing downhill, right? When you have -4 amps flowing uphill, you got 4 amps flowing downhill. That's pretty straightforward. And this -16 volts means that which side is the high potential side? The minus side is the high potential. So I'm normally circling that, but this is the high side. This is the high energy side. So the top is actually 16 volts higher than the bottom, right? So that's what that actually means. And the current is flowing downhill through that device, meaning it's absorbing power from the current. Isaac? Is the higher V going to be whichever side the side of, no, it really depends on whether the, you know, it depends on what's the label and then what's the actual value of the voltage, right? I mean, if this is a positive voltage, then the high voltage side would be the bottom. Yeah. Say that again. The voltage. For A. Yeah. Uh-huh. Yeah. Yeah, basically. Is that what you're saying? So the sign of the voltage value tells you which terminal has the higher potential side. Yeah. Yeah, that's true. Because you can try it again right here on D, right? So for D, again, we're just looking at this arrow, and I mean this arrow and this plus sign, and what does that tell us? Passive or active sign? Passive, good. And you can abbreviate that as just like PSC if you want, passive sign convention. Okay, so therefore, P equals I times V, and in this case, V is -3, so it's going to be -9 watts. So what's happening with that device? It's delivering or supplying power to the circuit. And what's the direction of positive current flow? Down. And which side has the higher potential side? Which side has more energy? Yeah, this is the high side. So the current is being impelled to go to a high energy state through that device because it's adding energy to those charges. So it's like a water pump. Another good mechanical analogy of voltage sources, current sources, pumping water. Charge is like the water molecules. Okay, last two. The takers, passive or active, Isaac? Yeah, you can go ahead and do the first one, whatever. What's the passive or active sign? Yeah, because the arrow is going into the minus sign, right? And so the power is what? Minus V times I, or I times V, which is minus 10 times 10, so that's 100 watts, so therefore it's absorbing. Positive current flow is up or down? Down. And the high potential side is top or bottom? Top. See, you all got it. It's not that hard. Ollie, you can do the last one. Active or passive? Passive, okay. So power is what? Which gives us 144, right? Then what? What does that mean? It's absorbing. Direction of positive current flow. Up. Which one has which side is the high potential side? Yeah. Yep. Those are good. So you're all going to get perfect score on those quiz questions. So the reason this is pretty important is like if you want to do things like conservation of energy, you know, well, the algebraic sum of the power for all the elements in a circuit at any time has to add up to 0. If it doesn't, you better run, right? Because something's going to blow up. Sum of all the power is 0. So in other words, you know, the battery's adding power and the resistors or the light bulb is absorbing power. And it's just the flow of energy from one point to the other. Energy is conserved. Speaking of energy, energy is the capacity to do work measured in joules. Energy absorbed or supplied by an element from T0 to T is an integral of power. The relationship between power and energy is that energy equals the integral of power from some time T0 to time T. And since P equals V times I, you can integrate the product of those two to find the energy. It's an integral. So example 3 says you got an energy source forces a constant current of 2 amps for 10 seconds to flow through a light bulb. If 2.3 kilojoules is given off in the form of light and heat energy, calculate the voltage drop across the bulb. Okay, so we are given I equals 2 amps. And delta T is 10 seconds. And also, it's telling us a little bit about the energy, right? The 2.3 kilojoules is given off in the form of light and heat energy. And is that power or energy? What is it still equal? as energy, right? So that's our change in energy over those 10 seconds. And we're supposed to find V. And the answer is supposed to be 115 volts. Well, okay, how do we find V? Well, we know that some formulas that could be helpful is that P equals I times V. And therefore, V is P over I, right? If we knew the power, we could figure out the voltage. And we also know that P equals, because of that integral relationship, P equals delta W over delta T, doesn't it, right? And we're given both delta W and delta T, right? So it's 2.3 kilojoules in 10 seconds gives us, what does that give us? I have a 2.3 kilojoules, or just 2,300 joules, right? So that gives us 230 what? Joules per second, and a joule per second is a what? It's a watt, 230 watts. And that equals 2 amps times V, right? So therefore, V equals 230 over 2, or 115 volts. How much energy does a 100-watt bulb consume in 2 hours? How much energy? Okay, well, again, energy is, so W is the integral of P times dt. And it's a 100-watt bulb, so what is that? What are we given here? We're given that P equals 100. And T equals 2 hours, or more conveniently, 3,600 times 2 seconds, right? So the integral of this, but it's 100 watts, it's constant. So the integral is pretty much the, just the area of a rectangle. So that's going to be P times T, right? Equals 100 times 7,200. So that gives us 2 more zeros, 72,000. So that's 720 kilojoules. Or, the power company bills you in terms of kilowatt hours. So you can just multiply 100 watts times 2 hours, 200 watt hours. That might be easier for calculating your power bill, David. How do I know the integral gives us power times time? Because in this case, the power is implied to be sort of fixed, right? So you're sitting here where P is here at 100, and this is going for 2 hours. That's what I do. And we want to find the area under this curve, right? So it's 100, which is P times T. So basically when the power is constant, it's just P, I guess I probably should have said delta T or something. P times delta T. The change of time that you're looking at the thing. Yep. It's the area under the curve of a constant. Mm-hmm. Okay, we're going to go into those different circuit elements tomorrow. And then we'll be getting close to doing some in-class problems. Yep. Okay. Oh, that sucks. What class is that? Yeah. No, I don't care. No. I mean, obviously, the course is available for people to just not do that anyway. But Scott will be there. I'll be there tonight. And whenever you get there, you know, whatever questions you have, kind of hash them out with him. Yeah. Yeah, you should pretty much have wrapped up homework 1B. Yeah. Well, I'm not collecting it. I'm not collecting homework at all. But the quiz is going to be on Monday. Monday. Yeah. But you want to pace yourself. You don't want to leave it all for the end. Yeah. Yep. Good. Sounds good? Yeah, I know. It's too bad. Luckily, you're going that way. It'd be harder to go the other way. Traffic will be fairly straightforward. No, coming at rush hour, going from Marina to MPC. MPC is a lot easier than going the other way. There'll be a lot of traffic flowing out of Monterey. Yeah, yeah, you'll go fast. Yeah. For materials. Yeah, different class. I'm collecting it for this class, yeah. Yeah, you can either do it electronically or, so if you're an online student, you have to scan it and submit it to campus. But if you're in class, you can turn it on Monday. Yep, yep.
I have a 6th edition of yeah. Is there like a 4th edition of the library so we can
I think it's the 3rd edition in the library, unfortunately. But you can get it. You can download an extra key for the 4th if you want. Yeah.